Thank you, everybody, for coming. So today we're going to take a little bit of a journey. We're going to see a little bit of the history of data control, and then we're going to move into a case study, what we've done at Frequency to make data control more possible in social graph, and then we're going to take a little peek into the future, the most fun part, and see and imagine kind of what new technologies are coming, what are their limitations, and where are we actually going with making privacy more possible in today's decentralized world. So first, let's start off with data control itself. What is data control? Why do we care about it? What is this thing? And I would say it comes down to really 4 different classic pieces: create, read, update, delete. If you are used to a lot of application development or standard kind of database, this is your old CRUD, C-R-U-D. And each one of these pieces has a different piece of data control. The ability to create new data, the ability to change that data. Do you really want anybody just going in and deleting your personal information? Probably not. So you want to control that with these 4 pieces. And these 4 pieces each have a kind of corollary in decentralized systems. So create, we've got that pretty well solved now. That is kind of this authorship validation. Signatures, the private key system that has worked really well in most decentralized systems, allows us to know that when I create something, everybody knows that it's me, and you can't create something for me unless there's a system that allows for that. We're going to skip over read for a second and go to update, right? This is the logic of the blockchain or the decentralized system. The allowance to update, usually also still kind of going back to, do you have that key? Do you have those permissions? But the logic of the system allows for lots of different people to do updates in different ways, but limits those in the way of the system. Similarly, delete is a little bit more complicated, but it has the logic there itself. But in decentralized systems, we also have to deal with the fact that once you delete something, you actually have to remember that you deleted it, or else you might re-add it. And so we have a system called tombstoning that allows you to identify data that's supposed to be deleted, but you have to remember that you deleted it. Now, obviously, we missed one important piece on this puzzle, the read, and that's because for the most part, not entirely true, but for the most part in decentralized systems today, that read capability is entirely public. We don't do anything to limit that necessarily, and we don't interact with it because of the needs of the decentralized system to have that data flowing, to be able to prove the system as a whole and to interact with it. So, let's take a look back at history and see if it can tell us anything about where we might be going. We'll look at probably the most successful decentralization system itself, the internet, right? And how did the internet develop data control? What stages did it go through? And that first one, very early in the internet, it was physical access controls. Do you have access to the computer lab? Well, if you do, then you have access to the system. But if you don't have access to the computer lab, which was most people early on, then you just didn't have access. Very quickly, that stops working, right? You get a certain number of people that have access or want to have access, and you need additional pieces. So you get user access controls. Okay, we've got user access controls, so it's still important to lock up the computer lab, but we're starting to get there where people are independently identifying themselves onto the larger system. Then we needed a way to do larger things. We wanted to do encrypted communications so that we could do fun things like e-commerce. Great little thing to be able to do. And so I don't want my private financial information just going across the internet in plain text. That's okay if it's just reading a paper that somebody posted, but it's not very nice for my financial credit card information to be just available out there. So there was a move to encrypt the communications. And then finally, we're starting to get to the point where the data itself at rest, especially in the case of healthcare information or other sensitive information, it starts to be encrypted at rest, or even in peer-to-peer, we have encrypted communications. The wonderful thing about this whole story, though, is if we look at the time period from 2015 to about 2020, we have the great encrypting of the internet. Before 2015, and I'm exaggerating a little bit, most of the sites that only used SSL for encryption over the wire, those sites were e-commerce sites or specialized websites that needed that security specifically. But through a bunch of technological changes, bringing down the costs of using encryption due to new entries and a lot of advocacy groups, the advent of Encrypt Everything and all the other various ways that people made it easier and easier to encrypt things, in a mere 5 years, over half of the internet traffic that was not previously encrypted became encrypted. And today, it's very rare to find yourself going to a non-SSL encrypted website. This is an amazing thing and applies now to not just sensitive information, but you're going to Wikipedia. That act, the contents of Wikipedia are not sensitive per se, but it's privacy that what you're actually getting from Wikipedia is now encrypted and can't just be inspected by your ISP or other members of the internet. So, what about blockchain, right? And we remember this. We had the read capability. It's public because, you know what? Etherscan shows it all, pretty much. And we know from research that even a lot of the pseudo-anonymity that we get out of the financial transactions happening, a lot of those tend to be a lot more de-anonymizable than maybe we once thought. And researchers are able to identify, okay, well, we know this happened, we know this person knows this person, and you can do a lot of network and graph analysis of the movement of those financial transactions and understand not necessarily the specific individual, but oftentimes companies or larger individuals on the internet and on the blockchain. So, where are we today? Today we have a lot of encryption, a lot of easier to use encryption. We have a lot new pieces of privacy and ways to interact. We have TEE and we have zero-knowledge proofs, and encryption has become easier and easier and more common, and much more common for people to say, hey, there's a feature of this application. It's end-to-end encrypted. This future is pretty bright, I'd say. And as a case study, here's what we had to do on Frequency. So Frequency hosts various protocols, but one of those protocols is a social media protocol that enables people to do things such as store their private graph on chain and make it portable between different applications. Almost 1 million private graphs are already on Frequency. So let's dig into a little bit of the details of how we did this. So first, back before we had it, it was a question of, do we even need this thing, this private graph? Why is privacy important for the social graph? And so the first thing we thought about was, well, you call them your social connections. That implies that they're yours, right? That's kind of a silly thing to say, but not everyone understands that, in that the companies you may go to may be like, well, that's my Facebook social graph. That's my Meta graph. It's not your graph. But anytime you offer those kind of social connections from your social graph to a company, the permission to read that graph is a permission to exploit the information therein. Imagine for a second that your social graph that you follow, say Vitalik and you follow Gavin. That kind of two relatively simple follows. You're following two people, but that tells me a lot about you just from that two pieces of information about your social graph. I can imply that you're probably interested in Web3. And we can go even one step further, right, and say, well, let's say you're not following any fancy Web3 people, but all your friends do. And if all the people that you follow those people, we can start implying that you probably may be interested in this Web3 thing, or at least a lot of your friends are. And so this social information, this graph, exposes a lot of information about you. Finally, we have the trust aspect. In kind of this blockchain system, a lot of the information flowing into it is effectively a version of radical transparency. It's not that you should, only share your financial information with this one company and your transactions with this one company. It's just share it with the entire world. And so we're going to go to the bottom of the barrel and make sure that it's exploitable by everyone. That's better. Well, maybe that's necessary for something like financial transactions that have their own systems and regulations. But with something like social graph, would you really trust that every single company in the world can sit there and consume your data about your graph and then proceed to exploit it? Instead, a lot of users have opted for the idea of, well, I don't really like this major social media company, but I'd rather trust just them than having everyone out there have my social information. So on frequency, we started to take this idea of privacy and, okay, we want to do privacy. How do we actually physically do it? How do you consider the ownership and the data control around private graph? So the first, there's a couple, whoa, we missed a couple pieces in there. Yeah. How did we approach this shared nature of social graph? Well, first off, there's two different types of social connections we're kind of most familiar with in the internet. One is follows. The skater wants to follow the cyclist. That makes sense. And it makes sense to us that it's the skater is the one that kind of owns that follow. Now, the cyclist might have some responsibilities and abilities to block or limit the ability of the skater to do this, but we can kind of pretty much say, okay, the skater kind of owns that follow. They're the ones in control of if they are following or not following the cyclist. Pretty nice. That's relatively straightforward. The skater only needs to know that information. We're pretty good. But when it comes to kind of bi-directional, friendship-type connections, wait a second, we have something here that's the two of them have to opt in together. Maybe we have a Romeo and Juliet across the different wheeled conveyances. Great change. And so these two want to be able to know that they're still friends with each other, but neither one of them explicitly owns the whole relationship, right? Because either one of them could break the relationship and say, we're not friends anymore, and then it doesn't matter if you say we're friends. If I don't say we're friends, then I'm sorry, you're just deluding yourself. So, how do we actually take this? We took it and broke it down into first the two pieces, right? Okay, I follow you, you follow me. Is that enough to form friendship? Because it's pretty clear that, okay, my connection to you is mine, your connection to me is yours. That makes sense. But again, that doesn't tell me, especially if it's private that you're following me, it doesn't tell me that we're friends. I don't have a way to confirm that we're still okay with this. So we have to add an additional kind of piece of information there that says, okay, I can know that I'm friends with you, and I can verify that you're still friends with me. Now, we did this in a couple technical ways, and I'll skip over too many of the details, but effectively, we generated a pseudonymous relationship identifier, something that uses the cryptographic primitives to create something that allows me, as, say, the cyclist, to confirm that you, the skateboarder, are still in a connected relationship. And this might look a little familiar, a piece of private information, a piece of public information. That sounds a whole lot like public key, private key setups. And indeed, it follows a lot of that and requires some of that infrastructure to exist. Now, I'm not going to go through the whole algorithm. You can look at this or look up the DSMP specification for yourself. But effectively, it uses those cryptographic primitives to not only encrypt the data itself, but also to allow for this kind of knowledge transfer across the wire without displaying any additional information to others. Now, we have to also say it's a lot of data, right? You're storing almost 1 million now, but potentially hundreds of millions of social graphs. How do we do that? So we've got the data itself. We know how we're going to store it. We know how we're going to keep it private and make sure we can still verify relationships. But the next step is, how do we actually store this data? And there's a lot of different pieces that go into making this happen. We try to minimize the data. We actually have an abstract account system that specifically uses 64-bit identifiers because they're so much smaller when we start talking about this much data. We make sure to compress the data, and we chunk it, and we place the data in child trees so that we can have a short and long state tree and Merkle tree. We require that information to be in state so that we can eventually get rid of historical data, because we don't want to keep around your changed social graph for but so long. Each of these pieces kind of plays into the technology that Frequency has to use in order to store all of this private information. And finally, the old classic problem of any encryption system: how do you store the key and how do you rotate the key? So we have, fortunately, a system to distribute the public keys. The blockchain works very well for letting everyone know that something changed. But we also, right now, are using just wallet encryption. The wallet stores that encryption key and is able to, through a sign-on with frequency standard that extends the EIP 4361 and CAPI 122, allows at login time for an application to say, I please would like access to your social graph, and then you can confirm that that access is allowed. The updating is lazy for applications, because if you rotate your key to remove one application, you have to then let the other applications eventually know that new key data. All right, we're going to go on a tangent alert here, because information theory has a lot to say about what we can and can't do with data. So one key, easy example is that you cannot prove that you don't remember everything I've just said. Now, I don't expect you to actually remember everything I've just said, but information theory says you can't prove that you don't remember it, because there's no difference between you lying about that you fell asleep during my talk and that you actually remembered it all. So we have this kind of problem about trust and where we're moving. As we share, once we share the social graph with someone, it's impossible from a information theoretical, from a physical world perspective, for that application to say, well, I've deleted your information, I don't remember it at all. For that, we have to move into the realm of regulation and governments and the rules that they provide to make sure that that data actually gets forgotten. This means, in the end, we can offer choice in which applications and who you want to trust. We can limit the amount of trust that's required. We can make sure there's requirements around it from a government standpoint. We can make sure that you understand the terms and that there's pre-commitments to allowing you to move your social graph and such. And we can control some of the consequences of broken trust. But at the end of the day, you still have to trust the applications that you're using. And this is what Frequency enables you to do, is make sure that you know which applications you're interacting with, and you're forming those relationships with those specific applications and companies. All right, from the case study and on to the future. Magical future, where we have a couple different technologies that I think are really going to impact how we interact with encrypted data going forward. So the first one is the one I'm most excited about when working in Frequency. This is a solution to a lot of the key management problems that you end up with, and that's threshold cryptography. At a technical level, it's just nodes that exist in the same kind of decentralized way that you expect a decentralized network of nodes to work, such as validators, and they provide some cryptographic primitives to you. But what this actually means, right, is imagine a situation where users need only worry about kind of the proof that they have permission to read some data, instead of having to worry about maintaining those keys. In reality, this means that we can switch from I need to give you a key to read some data, to I can say to the blockchain logic, okay, you have access to read this data. The threshold nodes themselves allow someone else to then go and say, hey, I am that person. per the blockchain, I have access to that information. Give me access to that information. So we're able to move to effectively a system where read permissions are capable in a decentralized world. That's pretty exciting, and I am really looking forward to seeing this as it grows, because it is viable right now. People are building this, people are using this, and the primary limits, though, are limits that we're used to in a decentralized manner. How do we deal with collusion? How do we deal with Sybil attacks? Because indeed, if you can convince enough of the threshold cryptographic nodes that they should give you information that maybe they shouldn't, then you can still get access to that information. But we're already used to that in the blockchain world, in that if you convince enough miners or enough validators that your transaction is valid, then you're pretty good. Another technology coming is homomorphic encryption. Now, this is calculations and the ability to do transformations on already encrypted data without unencrypting it, without being able to see the plain text of the data. This is pretty cool. Applications can suddenly be much more blind to the information while still providing services. For example, wouldn't it be cool if your social graph didn't have to be exposed to an application just for you to follow or unfollow someone or to consume that information? Now, this is indeed working right now, but for general purpose homomorphic encryption, it's still extremely slow and expensive. There are some very specialized cases where it's in use, where the problem is able to be narrowed down, and I don't know that it's ever going to be fast enough for general purpose applications. Also, in some cases, you're just not able to do it without leaking metadata. We haven't mentioned metadata up till now, but there's an entire problem around, well, what metadata do I know about you so that I can, even if I can't read your information, I can read enough about that information to infer certain things about you. For example, if you are transacting on Ethereum every night at, let's say, 10 p.m. local time, it might be possible for someone to start understanding, oh, well, you're maybe in this time zone. You're probably not in a time zone where that action happens at 3 a.m. So the metadata around all of this is a problem, and homomorphic encryption has a metadata problem that it has yet to deal with in a lot of ways. All right, PassKey encryption. Everybody's talking about passkeys these days. Encryption in PassKey, there's a PRF extension to WebAuthn. This is actually available right now on some browsers. They already have this. And it's the ability for devices to provide on-device encryption primitives to websites and applications. This is also pretty exciting, the idea that I can create an application that does a form of end-to-end or end-to-database level encryption, where you indeed have access to that data. You can use the PassKey primitives and the most major operating systems capabilities to kind of share those between different devices to allow you to have that data on demand. It's still very limited in its support, and it requires a lot of trust in the PassKey system, the application. Do you really trust Apple or Google to store that data and not look at it? And do you actually trust the client itself from the application? Because at the end of the day, you are an analog being. Turns out, right now, that's still true. You are analog, which means you can't read encrypted data. You still have to read the plain text data, and something has to show you that plain text data. Do you trust the thing showing you that plain text information? I hope so, because it's going to be able to see it. And hopefully it's not some, Signal alternative or Telegram alternative that's sending that information off to another server. Alrighty. PassKey also has the problem that it's sandboxed to a single application. You can't necessarily, right now at least with the current implementations, you can't say, I'm going to encrypt a piece of data for application A, and then I want to reuse that data in application B, because application B, even if all of the systems are working correctly, application B won't have access to that decryption key. Alrighty, one more, the one you always have to talk about when you're talking about cryptographic primitives and the future, and that is quantum everything. The quantum world is theoretically coming. It's another 5 years away, and in 5 years away, it might still be 5 years away, but it is slowly coming closer. And imagine a world where quantum computing doesn't. It comes and we still don't completely break all the cryptographic primitives that we're used to. There are indeed some cryptographic primitives out there and some algorithms. The NIST has some both encryption and signature systems that they have authorized and kind of started promoting as quantum-safe systems. And it is working, but it turns out it's a lot more expensive. Here's a quick little view into how expensive it is. On Ethereum or on Polkadot, you have 20-byte or 32-byte public keys and addresses. Okay, that's not too bad. 32 bytes, let's say, 20 bytes, that's fine. The smallest of the quantum-safe algorithms for signatures has a over 1,300-byte public key. So that's 65 times more than your little 20-byte Ethereum address. Now you can imagine that with hundreds of thousands and millions of different addresses being in your database, that if you were to use the full quantum-safe public key, you're going to increase that size of that database by 65x. That's a lot of additional data that you're actually talking about. So that's just a quick example about the limits that these new quantum methods allow, but at the same time, they are there, they are viable. I also suggest that they're new. Using novel, new cryptographic primitives is a very careful thing that you have to do because they aren't as well tested, right? A lot of the cryptographic primitives that are in wide use have been tested, they've been researched over and over again. Several different vulnerabilities might have been fixed. But at the end of the day, these are expected to be the new cryptographic primitives that we might have to use one day. So, with all of this, we have kind of taken this tour of the history of where cryptographic primitives have come to the internet, how we have kind of case studied, looked at it in frequency on the specific use case of social graph, and kind of this cool future that things are going to make possible. At the end of the day, it comes down to this wonderful quote from the Universal Declaration of Human Rights. No one shall be subjected to arbitrary interference with his privacy, family, home, or correspondence. Right? This idea that privacy and data control is actually a human right. And it's our responsibilities as the technologists and the builders to make sure that these human rights are still capable and possible and available and usable in the new world that we're moving into. So, with that, thank you very much for listening to this log arc of a story. You can learn more about frequency at Frequency XYZ, the DSMP specification, dsmp.org. And if you're taking pictures of slides, there is a PDF of these slides available on slides.willwade.com. So all those fuzzy pictures you took, you could kind of just delete those and save that space. Thank you very much.